we're live from BBC. BBC
That's good.
Guys, what we're going to do today is we're going to finish off on graphs and then move on to calculus. What I would like to do is to finish off with one final example, and I hope you've all got some graph paper, maybe sharp pencils, rubbers, all that sort of stuff. Okay. No, that's why you've got the rubbers with you, at least maybe an eraser. L and T are related by the law. L equals R times T to the power of P. So R is a constant and P is a constant. An experiment has been conducted where values of L, 3 through to 10, generated values of T, which are shown on the board, 0.383 through to 21.206. Since they all line up. Yeah, they do, yeah. Okay. Now, what we have to do is reduce, or using logarithms, we can reduce the information to a linear graph and extract information that gives us the values of R and P, so we can actually find what the law is relating them. But what we have to do now is to find what is it that we have to plot against plot. And that's probably the hardest part of it. The other day there, we looked at y equals mx plus c, and so that's what we have to do with this. We have to look at how we get the equivalent y equals mx plus c. Whenever we see this power, that should tell us the first thing you're going to do is establish log relationship somehow. We take logs of each side. So whenever we take logs of each side, we get the log of L equals log of R T to the power of P. And if we work our way through that, guys, what we do is we get log of L equals log R plus P log T. You guys maybe take an extra 2 or 3 steps to get to that, but this is what we end up with. We're looking for the form of y equals mx plus c. And so I'm now going to rearrange the log equation to give me log L equals, well, m, the gradient is a constant in a straight line. And whenever we actually look at this, what we have is p log t. T is a variable, x is a variable, p is a constant, m is a constant. So it's p log t would be the equivalent here, plus log r. So what we're going to do is we're going to plot log L versus log t. Similarly, from the graph, that m will give us the direct value of p because it directly equates m to p, and c, the y-intercept, as we call it, is the equivalent of log r. That means that r is 10 raised to the power of c. So we find c and raise to the power. So what we have to do now is establish our table, and we have log L and log t. And in true Blue Peter fashion, I did it earlier. Okay, so let me just fill in the numbers. Now you guys can double check these numbers just in case, okay? You believe me, then? You're so trusting. You're the only one who does. Okay, and now the column for log t. Okay, so we've now created the table. There's one other piece of data now that we have to generate because it's experimental data and it requires us to draw a best fit straight line. In order to draw our best fit straight line, we use a centroid. So a centroid for log L. So the sum of log L divided by 8 gives me 0.795, and the sum of log t divided by 8 will give me 0.802. So our best fit straight line will pass through that centroid. So what I would like you guys to do, now I've done all the hard work, is that I'd like you to now plot your graph and establish your y-intercept value and your gradient from the graph. It's going to take you a few minutes. Now, guys, you have to remember that your graph, whenever we would look at it, and I actually did do it earlier, the log L values are all positive, so you don't have to worry about anything below the horizontal axis. You put one piece of data on the negative part of the log t axis, so the majority of it, well, everything's above the horizontal axis, and the vast majority is to the right of the log L axis as well. Lay it out and you should actually occupy the majority of the A4 sheet of your graph paper. And I'd like to see you guys have a go at that. Yeah.
So log L is horizontal?
The log L is your vertical axis. It says plot log L. It's always your vertical axis versus your horizontal axis. Any questions then? Apart from John asking, how do you do this?
How did you decide which log to use?
How did it decide which? What do you mean, Sean?
Log L.
No, go ahead. No, go ahead.
This whole stuff right here is absolute confusion.
It's confusing you. Okay, right. I've told you this law. Yeah, I've given you this law, and I've told you that R and P are constant. There's two variables here.
And do you always tell us what's going to be constant?
Yes.
All right.
Yes. Otherwise, how are you going to know how things are related? It would be a very, very difficult task. So I tell you what are the two constants, but I don't tell you what those constants are. We know that one is gradient in some way, and the other is related in some way to the y-intercept. But it's the relationship, how you actually establish those values. That's what we have to work out. And in order to have a straight line, you have to have it in the form of y equals mx plus c. That is not of the form y equals mx plus c. L equals rt to the power of p is an exponential. It's not.
So,
Okay, so we have to rearrange it.
see that R and that P,
Yes.
and them number letters will change. Like, say if you're giving us a question, would that be like D, T,
Oh yeah,
the power
yeah,
Z?
yeah,
And
yeah.
the T always
Yeah.
stays up.
You can call them Johnny and Freddie. They're just symbols, okay? But they are the constants. And bearing those in mind, you say, right, okay, one of them is a gradient, one is the y-intercept. The gradient is always associated with the variable on the horizontal axis, always, because it's mx. So what you do, you have to rearrange, you have to take logarithms of each side. Now that is the rule, you take logarithms of each side whenever you see a power like this. So log of L equals log of RT to the power of P. Well, that's the same as log R plus log of T to the power of P. But I've just taken the shortcut that that's the same as P log T. Okay, it's your basic rules of log, or indices and logs. So log L equals log R plus P log T. Well, log R is a constant, so the log of the constant is just a constant. It doesn't alter much. There's nothing else associated with it. So you know that is your y-intercept. That's how that's related to the y-intercept. Similarly, P is a constant times log T. Log T is a variable. The log of a variable is still a variable. So a constant times a variable. And whenever we look at y equals mx plus c, m is your constant, x is your variable. So we match m to p and x to log t. C is matched to log r. And so that's why I've rewritten it in this form here, so you can actually see it. And that tells me now that I plot log L against log T. Now, in the exam, guys, I give you a hint. The hint is, this is what you plot. Okay? So you plot, I'll tell you if you have to plot log L versus log T. So I'll tell you, do these calculations and plot them. You have to still establish this relationship somehow to extract the value of R and so on. So you still have that bit of work to do, but I'm giving you a very strong hint as to what you should do. Okay. So it's now a matter of plotting this on your graph. And whenever you plot it on your graph, that would be my axes. So log L, log T, and we have something of this nature. Everything's above the log T axis, so I can forget about what's down below there, so to try and maximise what's on my graph paper. And to establish this value where the graph, the best fit straight line, will cut the log L axis. So we establish this value and then raise 10 to the power of that value to give us R. But we still have to calculate the gradient. I see a number of you are using your graph paper in portrait style. Whenever you use it in portrait style, if you actually change it through to landscape, you find that you actually get a better use of the axis, better scales. But again, that comes with experience and practice. It does. Okay. Now you'll not go wrong with doing it in portrait style. But your accuracy might not be quite the same. Okay. But it's like everything else, it's practice makes perfect. So that's what you could all be doing on St. Patrick's Day. Yeah. I can just see John now with his big graph book and very sharp pencils. Huh? I hope so too. You walked into that one. 0.6.
Guys,
Guys, 0.6, 0.78, and when I actually look at my straight line, I get 0.6.
That works.
And actually does sit on the straight line. Yeah. Sorry guys, I wasn't seeing the numbers.
Scott, that's what you okay?
No, actually this is valid from my point of view, because I can look at that and go, Jesus Christ, get it right next time, guys. You know, it's all part of reflecting on real practice, is how I would describe it. So, right, the main thing is, you guys are all able to do your calculations, that's the main thing. You're able to actually plot them and challenge me on them. And to me, that's perfect. That means that one or two in the class actually know what I'm doing. I'm not looking at John in that sense, okay? Because I know it doesn't apply down there. Don't worry, John, I'm not joking. He pays me to give him abuse. So, you've managed to plot a straight line. Okay, so if you've managed to plot the straight line, what value of y-intercept have you determined from your graphs? What is the value of C?
0.62.
So, Cal's saying it's 0.62. Any other takers? Sorry, 0.602. Did I hear? Is it 602? Oh, sorry, I picked you up wrong. Sorry. Okay. Anybody else? Any other numbers? How did we find it? See when you draw your straight line, you see where it cuts that vertical axis?
Yes.
What value can you read from your vertical axis at that point?
0.02.
No. Where you're looking at your graph paper, the graph, your straight line passes through the log L axis. At what point does it pass through?
That's 0.602.
Does it? Right, that's fine. That's what we're asking for.
That's up to 4.
Sorry?
That's up to 4.4.
Imagine that.
On all the way.
But did you actually get that on your graph paper?
Close enough, isn't it?
That's, sorry?
Close enough.
Close enough, yeah.
It was just
Yeah.
in the back door.
Because after all, that's the thing. These are calculations. But you're actually plotting it on graph paper, and depending on your axes and all the rest of it, your scales and so on, you might actually get it right. You might actually be a little bit out. So, that's why graphs are an estimate. Okay, so you've got C is equal to 0.602. So that means that R equals 10 raised to the power of 0.602. So R equals Can everybody have a go at it? Actually, use those little magic boxes that says Casio FX. Yeah. If you don't practice it, guys, you forget it. It's like falling off a bike. If you don't do it too often, you forget how to do it. 4. Okay. So we get R is equal to 4, and M is equal to what? It's the gradient. So what gradient did you get for your straight line? How do you do it in the calculator?
Put 10 and
Basically, you'll see on your calculator you've got the log button. So if I press log, oh sorry, clear that. Press log, oh sorry, not log. Shift, log. You see that it gives you a 10, the wee box. And now you put in your 0.602 and press equals. And actually in this case it gives you 3.99994 or whatever. So it rounds up to 4. Okay, that's how I would do it. Okay, yeah. The next thing, your gradient M. What value of M did you calculate?
points off that there?
Well, what I would do, guys, we've seen that the line does pass through all the points, and you can only take points or data from the line itself. But because it passes through the points, the easiest ones to use would be your y-intercept, because it's just, you're subtracting 0, so that makes the job a bit easier in that one. And one of the other numbers, one of the data points that it passes through. So I would just go for m equals, well, you know it's passing through 1.326 and 1.00. Okay, so y2 minus y1, so it's 1.00 minus the value of y at the y-intercept was 0.602, divided by the x value is 1.326 minus 0. So it's going to be roughly 0.4 over 1.326. That's roughly a third. So 0.3.
0.33.
0.33.
Or 3 point.
Okay, let's take a vote on it.
I got 3 points.
So what have we got? We've got 0.3.
No, I got 3.33.
3.33. Can't be 3.33.
I just took the furthest away points. Or took number 5 and number 10 now.
Right.
Double right? Number 5, number 10.
So what numbers have you actually typed into your calculator? It's the log L and log T values we're using. 1 minus 0.6 is 0.4. 0.4 divided by 1.3, that's 4 over 13, or 1 over 3, 0.33 roughly. Okay. Anybody, any takers, any other numbers? 0.3, 0.3, 0.3, 0.3. Okay. Right. And that is equal to P. So if that's equal to P, then we can now state our law, because we have now calculated the values of the two constants. We've got L equals R, which is 4 times T to the power of 0.3. And that's the answer. That is the law that relates L and T for this experiment. Okay. So guys, if we were, say I was assessing this in an exam, then typically what you'd be looking at is maybe about 5 marks for the table. You'd be 5. You'd be looking at 11 marks for your graph. Not for this mess that I've produced, but the mess that you would produce. And in the graph, I'd be looking at scales and labels. 2 marks for that. Accuracy of the plot, so making sure all your data points actually plotted where they should be. That's another 2 marks. The rest of the 7 marks comes from extraction of the gradient and the y-intercept and matching it to this statement of the logarithms and so on, which is which, and so we can actually get the value of gradient, the value of intercept, the value of R, the value of P ultimately. Okay? So that's where those 11 marks would come from in that sense. Right. Any other questions? No? You're happy enough?
Yeah.
So you've gone through the process now, and you've seen the pain as well. Like for instance, when I get my number wrong, typing it into the calculator, then you can see the mess it can create. And that's actually a good lesson to learn. Is if you need your reading glasses like I do, wear them. I'm so vain. So anyway, that's enough on the graphs. What we'll do now is we're going to go on to the next topic. Okay.
Does any of the teams
I'll press stop here. Where's stop?